I think without further ado, I'll hand it over to our speakers this morning. Thanks so much.
Good morning.
Good
Thanks for
morning.
joining us, everybody. I would love to know what role you play in your organization. If you are a salesperson or a designer or an installer or an owner of a company, if you would just want to put in the chat what your role is, then it's interesting for us, but also we can tailor our comments to the folks that are on the call. Okay, so I'm Li-Ling Young, and Mary Jane and I are coming from two sides of Efficiency Vermont. I work mostly with residential single-family projects, and Mary Jane works mostly with multifamily projects and a bunch of other commercial buildings and other things beyond that. And today we're going to cover both single family and multifamily. Mary Jane will use examples of multifamily, but a lot of what she is addressing is equally applicable to single family, particularly single family homes that have a high performance enclosure and have a really low load, a low heating load, a low cooling load. All right, let's go to the next slide. So this is our agenda. I'm just going to talk a little bit at the beginning here about how heat pumps interact with our climate. And then the main part of what I'm going to talk about is using this NEAP visualization tool, which we'll get to. I'm not going to spend time explaining it now because we're going to do a deep dive in a moment here. And then I'm going to hand it over to Mary Jane to talk about specific applications. All right, so let's talk about Vermont's climate. It is cold here, that's true, but it's not cold all the time. And it's probably not as cold as most of us think. So these are our design temperatures, and these are the formal temperatures that are appropriate to use when determining the design load for our buildings. There's only one county in Vermont that is colder than -11 as a design temperature. So that's Essex County. And -18 is really cold, but that is only one county. And the amount of buildings that are being built in Essex County and the amount of buildings that are getting new heating systems in Essex County is relatively small. So if I see a whole lot of design work being done with a design load of -18 and colder, I know that people aren't using the appropriate design temperatures to calculate a load accurately. Most of our counties are either -11 or -8. Yeah, so that's everything else, including St. Albans, Lyndonville, Montpelier, Middlebury, Randolph. Those are all between -8 and -11. And then, of course, the 4 southern counties, those are the warmest, and they have a design temperature of -4. So I'm not going to spend a lot of time on this, but the design temperature is the temperature you use to calculate the loads. It is not necessarily the coldest temperature the people in that place have ever seen. And that's really important to adhere to the way that the load calculations were built. If you think that you're doing a better job arriving at your load calculations by choosing a temperature that is not the actual design temperature, you're not. So I'd say this is just an ongoing issue that we see people who feel like they're doing the right thing by choosing a more aggressive design temperature, but that's not the way to do design. It is the way to plan your life, but in terms of design, use the design temperatures out of ASHRAE. Okay, so that's the design temperature. So that's like the far end of the design. That's how we come up with the load. But in addition to the load, there's a consideration about how the cold temperatures are distributed across the heating season. And this is the piece that I think it's really important to take on board when we consider, well, how cold is Vermont? It's not that cold because 80% of our heating season is warmer than 20 degrees. So this doesn't have to do with the load. It's a question really that impacts energy consumption. So we're going to come back to that issue, but one, I would say probably Vermont is not as cold as we all think it is. And two, it's not cold. It's not that cold for very long. Most of our heating season is a much more mild temperature than anything close to our design temperatures. Okay, now I'm ready to go next. All right, so now if we think about a heat pump in that kind of climate, there are a few different metrics, a few different ways that we have of looking at heat pumps that help us understand how the heat pump is going to operate in those two ways that I just talked about. The design temperature, but then also the distribution of the temperatures across the heating season. So heat pumps are variable speed, but they're not infinitely variable speed. And some are more so than others. So some will vary their speed across a very wide range, and some will vary their speed across a relatively narrow range. However, within that speed range, an inverter-driven heat pump will be able to hit any operating speed within the range. It's obviously not going to be able to go faster than its top speed. And this is really important. It's not going to be able to go slower than its bottom speed, but within that range, an inverter-driven heat pump, which is the most efficient cold climate heat pumps that we see, those can, operate anywhere in there. Okay, so capacity maintenance is a question of what we think of as the capacity of the heat pump. How well do we hold on to that capacity as we get into the colder temperatures? And of course, this is very important in this climate, but in other climates, like it's not as important. But when we're considering which heat pump to select, a lot of people will look at capacity maintenance and say, I want a heat pump that will maintain 80% of its capacity, or 90, or 100% of its capacity at some lower temperature, at 5 degrees, or at -5 degrees, or at my design temperature in the area where I'm designing for. The problem with capacity maintenance is that there's all these different ways of calculating it. So you can see there in the first bullet under capacity maintenance that it says NEAP. And we're going to come back to NEAP, but that's just an organization. And they have these different ways of calculating. So they're saying the rated capacity at 17 degrees divided by the rated capacity at 47 degrees, that's one way to determine capacity maintenance. And because we're not, none of our design temperatures are 17 degrees, I don't think of that one as very helpful. And then there's the rated capacity of the heat pump at 5 degrees. Okay, so now we're getting a little bit closer to our design temperatures, divided by the rated capacity at 47. What we will talk about in just a moment here is that these rated capacities are kind of in the middle of nowhere land. Like I personally don't feel like it's that helpful to talk about a rated capacity because these are variable speed devices. Why don't we talk about the maximum or the minimum? Because that's really the limitation of the heat pump. And then you can see that there's even yet another way of determining the capacity maintenance, which is the maximum capacity at 5 degrees divided by the rated capacity of 47. And to me, I mean, we're getting a little closer here, but fundamentally the piece about capacity maintenance that I don't think is helpful is that it's always related to the capacity at some warmer temperature. And as a proportion of that, I don't think that that's really how we should be selecting our heat pumps. And we'll tell you in a moment here how we do think you should be selecting your heat pumps. Okay, so the next one is turn down ratio. The turn down ratio is just, it's just a ratio, but it's very similar to capacity maintenance. It's just another way of looking at these things. It's, the ratio between the let's see, it says here, minimum output compared to the maximum output. Okay, so now we're starting to get a little bit better because now we're not in that nowhere land of the rated capacity is somewhere in the middle, right? We are talking about actual limitations of the equipment, minimum and maximum. Again, I don't think turn down ratio is that helpful. It's starting to get a little closer to a way to evaluate heat pumps, but all heating and cooling loads are going to start at 0. And so, after it gets a little bit colder than our 0 load, then our load is going to be very small. So, we might have a load of 400 BTUs an hour. That is super tiny. And that might happen when it is 40 degrees out, or depending on your building, when it's 35 degrees or out or 55 degrees out. But all loads are going to start at that really super low level. And so even if you have a really nice turn down ratio, a good turn down ratio would be something like 7-1, which is to say that compared to the maximum output, the minimum output is just 1/7 of that. And that would be a really good turn down ratio. That has a very wide operating range for the heat pump. So it looks great, but if the heat pump is already starting out very large, then even that 7-1 ratio is not going to get you down to that 400 BTUs an hour. So what I think is really important to look at is the absolute minimum capacity. So not as a percentage of anything else, not as a ratio compared to anything else, but the actual lowest capacity. And the lowest capacity at the temperatures when what you need is part of the load. So lowest capacity at these warmer temperatures. So the reason that I went through all of this is because the short cycling that happens when you don't have a good match at these these low capacity in warm weather, that this, if like the lowest capacity at 30 degrees is say 4,000 BTUs an hour, and your building really, or your apartment really only needs, 500, then the only way to meet that load is for the heat pump to turn on and off, because it's going to overheat the space if it runs at its lowest speed. And that turning on and off really hurts efficiency. I say here that it can hurt efficiency, but it really, really hurts efficiency. Okay, so now we're ready to go on. Okay, so let's look at the NEEP database, and I say putting it all together here because now we've talked about the climate where our heat pumps are going to be operating. We've talked about how the heat pumps operate and how we can evaluate which heat pump might be suitable. So let's put those two things together. All right. So the NEEP cold climate air source heat pump list is just a database, or it was a database. It's more than that now. But it was a database used for utility programs all throughout the Northeast. So that's like New Hampshire and Maine, and I don't know all the states that are part of the Northeast Energy Efficiency Partnership. But it was for a long time only something that utility program administrators knew about and considered and referred to. And it was very helpful because there's a standardized data format so that heat pumps that were suitable for a cold climate could be compared against each other. And NEEP wrote a specification that was how a heat pump could be admitted onto the database. And that was a way for the utility programs to say, okay, things that meet the specification, so they're on the NEEP list, we'll pay an incentive on those. And things that don't meet the specification, we're not going to pay an incentive on that. So all of this is happening in the background, like, designers, building owners, nobody really needs to know about this except utility program people. But they added, let's see, this must have been in 2022, so it's just last year, they added a new feature to the cold climate heat pump list, and it's analysis. And it's analysis where you can put in specifics about your application. So, here's where the building's going to go. Here's the load of the building. And what I've heard from other people who use this part of the NEEP list is that sometimes they use it for sales, and sometimes they use it for design. And for Mary Jane and myself, we use it to help guide people toward heat pumps that are going to perform better in the specific application that they have. So this is like a huge change. Now this list that nobody was really going to refer to ever, not, nobody in the public, now suddenly it has this very powerful tool. And I have put the link down there. Bryn, I don't know if we're going to share these slides out, but even if you don't end up with that link, it's not hard to find the list. You're looking for the NEEP cold climate air source heat pump list. And it's easy to find, and and I'll show you in a moment here how to use it. All right, next. So this is what I call it, a visualization tool. This is what it looks like after you do an analysis. And I'm going to draw your attention to some things here. Make sure I move Mary Jane's head out of the way. Let's see, can I have a pointer? I don't think I know how to do a pointer. Can you see my mouse? No, because Mary Jane's driving. All right, so let's look at the yellow band in the middle there. The yellow band in the middle is bordered by a dark red line and an orange line, and then there's a red line somewhere in the middle. So that yellow band represents where the heat pump can operate. The upper part of the yellow band is the highest speed. And oh, I should say, okay, I'm sorry. Let me back up. I was actually thinking about this morning. How is it going to explain this? So along the x-axis, we have temperatures. And along the y-axis, we have two axes. One of them is showing BTUs per hour. So that's like the power of the heat pump or the capacity of the heat pump. And the other one is showing BTUs per year. And that's really important. So we're going to come back to that BTUs per year thing in a moment. Okay, so temperatures across the bottom, capacity and energy in the y-axis. All right, so back to the yellow line, the yellow band. In the yellow band, the upper part of the yellow band is the maximum capacity of the heat pump, and the bottom is the minimum capacity. And that red line in the middle of the yellow band, that is the rated capacity. And as I've already said, and I know Mary Jane will come back to, is that red line really has no relevance. It has no relevance for design because we're never going to design to the rated capacity. We need to know what the maximum capacity is, right? So that we know that the heat pump is going to meet our loads under design conditions. We also need to know what the minimum capacity is because of what I said before. If we drop below the minimum capacity of the heat pump in terms of what our space wants in heating and cooling, then we have very bad performance of the heat pump because it's not operating within that yellow band anymore. It's outside the yellow band. It has to turn on and off in order to not overheat or overcool the space. Let's see. So on the left here, you can see that the yellow band just stops. And that's because the NEEP list requires manufacturers to submit capacity and efficiency at 47 degrees, 17 degrees, and 5 degrees. And that's it. They don't require any other data to be in the list. However, we know that many cold climate heat pumps and the best cold climate heat pumps operate much colder than 5 degrees. And in general, I think of minus 20 degrees as being sort of the outer limit. There are heat pumps that will never turn off even at minus 20 degrees, but I think of minus 20 degrees as the limit of what a cold climate air source heat pump is going to do. So why do these just drop out to nothing over here on the left? Well, there isn't data in the database, so that's not going to be charted here, but the database has the ability, or the tool, the analysis tool, has the ability for you to put in more information. So if you know that this particular heat pump is listed by the manufacturer to have a capacity of, say, 10,000 BTUs an hour at minus 10 degrees, then you can put that data point in here and it will be added to the chart. And so this big cliff here at 5 degrees, now it's not there anymore because the dark red line gets extended out to the left. All right. So that's, oh, I keep forgetting that there's another. Can you advance, Mary Jane? Right. Okay. So I actually have some words to go here. So the purple area beyond where the yellow band is shown is considered unmet load, but that's just because in this case, I did not put in the extended information for this heat pump. You can see the max capacity, the rated capacity, and the min capacity are indicated within the yellow band. And then we'll get to this part in a minute, but that vertical line there is the design temperature. And that's something that you can enter into the visualization tool. Okay, now we're ready for the next slide. So everything that we've talked about so far, except the design temperature, is really about the heat pump. We haven't started talking about the application, so the building and the location where the building is. So now we're going to talk about different parts of this chart. This is a different heat pump. And in this case, I did go to the manufacturer's data, into their extended engineering data, and I found how this heat pump performs at minus 13 degrees in terms of capacity. And you can see that is a optional piece of information I added in there, but it now shows that instead of the capacity of the heat pump just dropping out when under a condition when I still need some load, instead it's showing that the heat pump can continue on all the way past my design load. So in this case, I've entered a design load at -5. Don't do that in Vermont because there's no place that has a design load of -5. I guess maybe those southern counties. But so the capacity of the heat pump is continuing on to the left, but you can see that there is a little slice here where, okay, well, actually, no, I haven't gotten there yet. So the diagonal line is, now we're starting to talk about the building. The diagonal line is the heat load of the building. And again, I mentioned this before, you're always starting at 0 load. So when it's warm out, your load is 0. And when it's 50 degrees out, your load is very, very small. So on the left, very small load. As it gets colder, the load of the building increases until you get to your design temperature. And that's the load that you're selecting your equipment around. You're selecting it around this load at the design temperature. Okay, so that's the load of the building. The piece in the back that's sort of behind everything else, these blue vertical bars, that is the BTUs that this building will need during whenever it is that temperature for that bar. And so remember, across the bottom, we have temperatures. And this is where we get to these vertical, the y-axes. So those blue bars are looking at the right axis. And the right axis is showing BTUs per hour. Thank you, Mary Jane. So what's really important to understand here is that these blue bars are not about how long we spend in that 25-degree situation or how long we spend at 10 degrees. This is showing how many BTUs this building will need whenever it's 10 degrees, and it's added up over the course of the season. So this is sort of combining the temperature and the load of the building. And this is really important to understand about this, is that these bars back here, they are a direct line to your operating costs in this building. So you can see that there's a big bulge of temperatures in the warmer temps, the big bulge of heating consumption, I should say, in the warmer temperatures. And remember what I said in that first slide, it's not that cold here for most of the season. 80% of the season is at 20 degrees and above. And so 80% of all of this energy is being shown consumed. It's more than, yeah, maybe it is 80%. I'm going to back off from what I was about to say. But in any case, you can see that most of the energy in the heating season is expended in these warmer temperatures. And although it's true that we need to design to meet the load of our space under our design conditions, which might be the design temperature and it might not, right? You might be designing for a space where you know that you're going to have an oil boiler kick on whenever it's 0 degrees or below, right? So in that case, you're designing for 0 degrees. So we do need to meet the load at whatever our design condition is, but at those really cold temperatures, we're not expending a lot of energy. So there's not a lot of expense for the building owner at these really cold temperatures. All right, so what else do we have about oh, okay, so the short cycling zone. So in this chart, we have this pink wedge here. And this pink wedge was added in by the NEEP people to show you when you have a problem with short cycling, because you can see that the green slope of the, oh boy, my computer is low battery. Well, I better talk faster.
Can you plug it in?
I feel like I'm plugged in. I'm definitely plugged in. Okay, I'm just going to talk fast.
Make sure your lightning cord is in the back slot, not the.
It is.
Okay.
There might be a catastrophe, but Mary Jane can pick it up when I drop out. Okay, so Mary, the pink we have a problem because the load of the building is below the lowest operating range of the heat pump. And if it's only like a little bit of the season, it's going to be not pink. But in this case, look, it's like 50% or 60% of all of our heating BTUs are being expended below this, in the short cycling zone. And that's a real problem. So I think we've covered everything on this slide. Yes, we have. Let's go forward. Oh, no, I'm sorry. Can you go back? Because I didn't talk about the table below. All right, so this little table down here is that comes in when you do the chart. It's kind of hard to see that the table pops in because it kind of looks like the rest of the but there's some really important things down here. So one of the things that you're going to get is Mary Jane, am I still connected? Because
I don't see your face. I don't see your face. I hear your voice.
Okay, that's fine. You don't need to see my face.
All right, there you go. You're back.
This is going to be really a problem. It will tell you how much of the heat load is not met. So this is a question of where the capacity of the heat pump is not high enough to meet this the demand of the space, the heating demand of the space at the design conditions. So it'll show you how much that is. And if you do some math, you can figure out what the cost of that is. You can, there's a bunch of information there that I have some notes about what I want to tell you, but because my computer is kind of freaking out here, I can't find my notes. But I think the most important thing here, well, actually, let's look at the bottom right. So the percent of annual load with low cycling. This is when they say annual load, what they mean is your cost, the BTUs that you're expending to heat the space. 50% of that is happening when the heat pump is not able to operate comfortably within that yellow band. And this is bad. This is saying we've got this great heat pump, high efficiency, it's variable speed, but we're going to ask the heat pump to operate outside of its normal range for half of our heating season. That's, you're not going to get good performance out of the heat pump under those conditions. All right. And so as you enter stuff into the tool, which we'll show in a moment, then these numbers will populate. And I just want to be clear, well, let's go to the next slide because I think I show how to use it.
I see some of your notes. There's this part here about the annual BTUs covered by supplemental heat. That could be your backup boiler, and that's that little purple area up there, or that could be electric heat. So you could easily do the calculation to see how many MMBTUs, converted to oil or converted to straight electric heat, how much you're going to spend on your backup heat. And that might help you determine if you want to go to a smaller system or to a larger system. And then down here, the percent annual heating load served is 93.9%. Okay. Are you there, Li Ling?
I am, but now I can't see anything. It hasn't been a great morning. Mary Jane, the next piece is just me use the NEAP tool, and you can do that part because you're
okay.
Yeah.
So the NEAP tool, once you get onto it and you you can search for the heat pump you want, and then you hit this advanced sizing. You have to hit advanced sizing, and then it'll bring up this information. And this is where you can put your weather station, your state, your design temperature, and what your space needs. And then down here you have, Leland, can you not see a screen?
I can see it now. It came back.
Oh, okay, go ahead.
Okay, so I just want to point out that the advanced sizing thing, it doesn't look like a button, but it's a button. When you push that, you get this pane where you can add in details about your your location, your system, your building. So when you select, sorry, no. Okay, when you select the state and the weather station, what it's doing is filling in those blue lines that are in the back. So it knows the distribution of heating across the heating season. The heating design temperature will drop in with some number that has nothing to do with anything in Vermont. So you have to actually you have to enter, like override and enter your design temperature for that space. Now you can add in here under design temperature, you can put the actual like ASHRAE design temperature for your space, or you can put something warmer. Like if you, in the situation that we talked about, if you have an oil boiler that you know you're going to turn on when it's 0 degrees or -5 degrees or 10 degrees or whatever, that's just part of your design, that you have this other heating source, then you can put that temperature in here and it will show you in that table how many BTUs you're going to need to use on the oil side. So, and then you put in your heating design load at your design temperature. And for the most part, if I'm assuming that people are designing to meet the entire load all season long with a heat pump. So in that case, your heating design temperature is those numbers out of ASHRAE that I showed on the first slide. And then your heating design load is the calculated load at that design temperature. And it should be just for the space that that heat pump is serving. Don't put, this 25,000, like that would be an entire house. Or yeah, it'd be an entire house. But if I have a ductless heat pump on the first floor and a ductless heat pump on the second floor, I'm not going to put in the design load of the entire house for each heat pump when I'm selecting each heat pump. And then these little checkboxes down here, you can, yes, so that lockout temperature, actually, this is where you can put in the piece about, we're not going to use the heat pump when it's colder than whatever, pick your temperature. And if you click that, you can enter in the temperature when you would stop using the heat pump and you'd start using some other kind of heating source. And then the second checkbox is where you can put in the information if you went and looked at the extended engineering data for the heat pump, and you can see that, at -11 degrees, it says the capacity is this. And you can add that in so that it will extend those capacity lines out to the left and show you what the capacity is actually at your design temperatures. And then the little button at the bottom, run sizing for heating data, you click that and you come up with the nice chart with all that information on it, and the little table underneath it with even more information. When I show those charts to people, I usually unclick the extra stuff. Like you can make the rated capacity line disappear. You can make a bunch of things disappear by unclicking them. And I do that because it's a very busy chart. But in any case, you get all this information and you can have less information if it's helpful. Okay,
so you actually just click on all these words and it makes the things disappear.
Yeah, and then if you
when
want
you're
to
in that
reappear,
graph. Yep.
Yeah. Okay, so where do you get this extended engineering data? This is just a heat pump that I, was just checking out, and I went to the Daikin website. I got, this actually is not like in their engineering manual. This is just in their sales brochures. So this one was pretty easy to get to. Some heat pumps manufacturers, they do not make this stuff easy. And some heat pump manufacturers don't publish this at all. It doesn't mean that they don't have a capacity below 5 degrees. It just means that they're not going to tell you what it is. But in any case, you can see there on the left, it's saying max heating capacity at -13 degrees. I do not care what the rated heated capacity is at -13 degrees, because at -13 degrees, I want everything that heat pump can give me. So the max heating capacity at -13 degrees, and then under that particular model, I was like, oh, okay, here we go, 16,000 BTUs an hour. And so this is the information that would go into that other screen that we were looking at with the lower checkbox. You add this information in, it extends the capacity line out to the left.
And that's a pretty good heat pump because you're not losing that much.
Yeah, you mean the capacity maintenance. That's what Mary Jane is referring to.
Yep.
Yeah. Okay, so that's the end of my part. I'm sorry for so much chaos there at the end, but now Mary Jane's going to take over.
Why don't we check for questions? Can Bryn or somebody look at the questions? There's six comments at least.
Yeah, absolutely. So let's see. One question that may relate to content you've had, what's the best way to locate outdoor heat pumps remotely and then use conduit of some kind to get into the house or building?
So all heat pumps will, there's pushing the refrigerant around by the force of the compressor. And so there's a limit with all these heat pumps about how far away the indoor units can be from the outdoor units. So that's one thing, is there's just a hard limit. Of course, you have to refer to the manufacturer's information on that. And then there also there's guidance on how protected or not protected, like how open the space needs to be around the outdoor unit. And so I think what I think when I'm looking at this question is, don't put the outdoor unit very far from the indoor unit. And I hear you that you are saying, like, maybe there's an application where you do need to put it far away. But in general, that's not good for the performance of the heat pump. You have to add more refrigerant with a really long line set, and you do lose capacity, actually, if you make the outdoor unit too far away. And then, of course, there's an absolute limit to how far away it can be. So in terms of UV protecting and hiding the exterior refrigerant lines, I would say conduit is probably going to be your best bet there. But the manufacturers of the heat pumps they'll let you know what you can put the line set in. And you might even have to refer to the manufacturer of the line set. So the stuff that you see on the outside of buildings, which is like preformed white plastic, that's called line hide. And that stuff is not designed for like ground contact. So if you're talking about anything besides like hanging it on the outside of the building, I would suggest working with the manufacturers of the heat pump or the line set.
And
There's also quite a bit of information on the internet about making sure you are sealing your insulation to the beginning and the end of the line set where it connects to the outdoor compressor and condenser, because there's a known issue with condensation getting up underneath, traveling underneath the insulation, and then there's a chemical reaction that happens that results in pitting, like by the time you get to year 7. We're already starting to see it happen on some older VRF and heat pump systems. So that's something you should really be paying attention to, either as a homeowner, if you're getting one installed at your house, or if you're an installer.
thanks.
Yeah, so it's corrosion, and you'll start losing refrigerant. That's how you would know that it's happening.
Yep.
And then you would have to replace the line set if that happens.
Yep.
So the insulation that surrounds the line set needs to be sealed so that no air or water can get into the end of the insulation.
Related to the first question, are there other factors to consider when placing an outdoor head?
Snow.
Yeah, snow. That was going to be yes. So snow, and also you don't want heat pumps blowing so the outdoor unit will bring air in, blow it across the heat exchanger, and then blow air out. And the stuff that's the discharge coming out of those outdoor units is no temperature that you want. In the summer, it's going to be hot, and in the winter, it's going to be cold. So you don't want the discharge blowing on any other heat pump. You also want to make sure that you're not creating a hazard by allowing the wintertime condensate off the outdoor unit to like dribble across a walkway where somebody could slip on the ice. Those are sort of the highlights about that.
Great, thanks. And there might be some other considerations depending on the utility. If you're in Vermont gas territory, you may want to keep you will want to keep the outdoor unit away from that meter as another consideration. So,
from
yeah,
a gas meter?
From the gas, yeah.
Okay.
Yeah, exactly. So next question. If anybody wants to, Leland through quite a bit on the NEAP charts. So if there are any questions there, you can certainly raise your hand or add them in the chat box. Happy to give some more depth of detail or walk through that a little bit more. But otherwise, Mary, MJ, if you want to
Sure.
move on to the next item, I think we're good.
All right, so we're going to talk. So my focus is more on multifamily projects and commercial buildings. And we're really struggling with, you wouldn't have thought 5 years ago that we were having a hard time heating and cooling super efficient buildings, but we're realizing now that these really energy efficient buildings are challenging because the loads are so small. We're not going towards the fin tube baseboard hot water where you could pick just a small section like we used to do. So now that we're sizing with heat pumps for these low load multifamily housing, we're finding that there are some challenges. So the first question is, how do you design a heat pump system for multifamily housing with very small heating loads and not end up with that short cycling that Li-Ling was showing on those NEAP charts and not have performance issues? And then the second is, what other products are on the market besides mini splits that maybe could solve this issue without having short cycling? I wanted to just give you a quick example of real calculations that have been done on multifamily buildings. So I have worked on tons of projects in Chittenden County as well as throughout the state. And I work closely with design engineers and was able to get some information from some of my colleagues in the design world. And they traditionally are using like HAP or Traintrace, Open Studio. I know on the residential world, Li-Ling, people are using Manual J. Is that correct? And so they're
In some
designing.
calculations, they use Manual J.
Yeah. So most people are designing for the -11 in our really cold kind of microclimates, like at the top of like Stowe Ski Resort, or because I do work with a lot of housing at these ski resorts. Those are microclimates that are even colder design loads, which are allowed per the energy code. These calculations are per apartment and they do not include the lighting and the plug loads and internal gains. Sizing for a worst case scenario, it's nighttime and none of these things are on. And all these projects have really fantastic thermal shells. Most of them are shooting for a 0.06 CFM 50 exterior surface area 6 side, which is a passive house number. Now we're kind of switching over to CFM 75 because that's what the energy code is using. And as you can see, these loads are really small, anywhere from 4,000 to 7,000 BTUH at this -11. And it definitely depends on where the units are inside the building, how much exterior surface area they have. So if you have a middle floor, a one bed middle floor with only one exterior wall, 3,300 BTUs at design, versus a top floor corner unit is 6,300. So it does make a difference where you are in the building. When designing with super insulated walls, really well done air tightness, what's happening is we're finding that the balance point, the point at which you go from heating to cooling, or the point at which oftentimes it's not an exact number because you've got like a buffer zone where you don't have heating or cooling. But what we're seeing now is that this balance point for heating is being pushed down. Normally, you would see something around 55 or 60 when you would start needing to heat. And now we're seeing it get 45 to 50, which is much lower than you would expect. On the flip side, because the buildings are so airtight, because the buildings are so well heated, they hold all this waste heat that could be coming from lights, electronics, refrigerator. And what it's doing is it's pushing down the cooling. So there is a positive impact from having super low buildings. One is you don't end up having as much heating. The drawback is you end up needing more cooling. And because multifamily housing can't do the economizer mode where you open up all your windows, there's just no cross ventilation when everyone has their own compartmentalized little apartment. You can open windows, but it's not going to do as well as it would in a home where you could open up from one side of the house and from the low part of the house to the upper part of the house. So it is having a negative impact. And I have some great data from some projects where you can now see this is a building that's electrically heated, meaning it has heat pumps. You can see now that air conditioning is starting as low as like 57 degrees. Even though the outdoor air temperature isn't very warm, it's all those internal gains. This is the negative impact of having a really airtight building. But on the flip side, you can see that like a real burst of heating doesn't really start until, like 42 degrees. Which is going to overall reduce the amount of heating that you need by having a better airtight building. Here's another example, and this is showing kind of a wider range of not needing heating and cooling. But again, your heating is really starting, this was senior housing, so you're going to see heating starting a little bit earlier. But around 50 degrees is when it really starts picking up and you can see the heating. And on the flip side, the cooling is pushed out a little bit because seniors have the tendency to not like as much cooling. It's not starting until like 68 degrees. So let's look at some apartments. When picking heat pumps from the NEEP database, there's a couple things that I wanted to mention in terms of what's available for selection. If you're looking at single zone non-ducted, meaning just one outdoor unit and one indoor unit, the smallest you're going to find is a 9,000. There are a few systems that look like kind of like a packaged heating cooling system, almost like what you would see in a hotel. They are available at smaller sizes, but those really aren't considered mini splits, but they are an option. And I'll talk about those at the end. And the smallest ducted systems are also can go down as low as 9,000. And in terms of multi-zone, meaning you would have one outdoor unit and like 2 or 3 indoor units, the smallest outside unit is 18,000. The reason why I bring this up is because in these apartments, if you only need 3,000 and the smallest you can get is 9,000, that's where you start needing to look at what Li-Ling talked about, which is how far can it turn down? And that's the critical part to look at in terms of making sure that you're a balance between meeting your load when it gets cold out versus short cycling. And most heat pumps are, they're going to be like an 09 or a 12 or a 15. And so that's your rated 9,000, 12,000, or 15,000. But don't get hung up on the rated number. And what, like Li-Ling said, is we need to look at what's the max and the minimum. So a typical 1-bedroom apartment, if I have a customer who's building an apartment complex and they're working with their design engineer and they say, well, I want to have heat and cooling in both my living room and the bedroom. This whole apartment was put into a load calculation software, and it was determined that they need 4,000 BTUs at -11. And you've got 2 indoor units, 1 outdoor unit, and the red lines is your backup electric resistant. The smallest indoor wall mount head is 7,000 BTUH. So right away, one indoor head is already more than you need for the whole apartment. And the smallest outdoor unit for a multi-head system is 18,000. So you're way, way over the amount of BTUs that you need for this apartment. And when it's 40 degrees out, you only need 1,000 BTUs, and your outdoor unit is able to give you 18, if not more. In general, we don't recommend this. So let's look at another option. Oh, first, let's see what this looks like. This option looks like with the NEEP database. I forgot that I pulled all that information. Okay, so I pulled the smallest outdoor unit is an 18. And here's the information on it. It's rated for 18,500. The max is 36. The min it can go down to is 4. So that's at 5 degrees, you can get 4,000 BTUs. I was able to look up on the internet what it would get at minus 13, and it gets 5,600 at 13 with a very low COP. I put all this information into the NEEP tool, and this is what I came up with. The yellow is the cone of performance. And this green line right here is my load. So this heat pump will be able to meet all the needs of this apartment. However, which is great, meaning there's no backup heat. However, look when short cycling starts. Short cycling is starting at like minus 3 degrees because this heat pump just can't go any smaller to meet the load of this tiny apartment. And the blue is when the majority of the heating is happening, which it's basically showing you're going to be short cycling during the entire majority of the heating season. In my mind, this is a no-go. This is not a good match for this apartment, and I would never recommend 2 indoor heads with 1 outdoor unit for something so small. So now let's look at another option. How about just 1 indoor head, 1 outdoor unit, and electric backup? This is a more typical design that I've seen for multifamily housing. There's a couple ways you can do thermostats. You can do a primary thermostat here in the living room from the manufacturer that allows for a secondary heat source to kick on, which would be your electric backup heat. And then you could have this bedroom be on its own thermostat, or you could have it tie in as the electric. When the electric backup kicks on in the living room, it'll kick on in the bedroom. These are the same numbers from before. And let's see, I picked a 06, which you would think is 6,000 BTUs, but the rated is still close to 9,000. So that's why I said the smallest outdoor unit you can get is 9,000. That's because even an 06 is still putting out a rated close to 9,000. This unit is great though. Look at 5 degrees. You can get 8,700, which is still more than you need. And when I put all the information into the tool, let's see what it comes up with. Look, the short cycling went all the way back to 36, 37 degrees, which still isn't great, but it's way better than being up here. Your yellow cone is where it's able to operate, and your heat pump is in your heat pump load, which is this line here. The blue load is inside the yellow cone. I put in the minus 13. You can see that number is right here so that we know what the heat pump is able to do. That was, oh, I don't have that number on here. Sorry. But I had looked that up, and that was where you are still, for a minimum, you're still within the yellow, and for the maximum, you're still within the yellow. So it's like 42,000, 4,200 at -13, -15 from manufacturer data. And that's still within the right amount of heat that we need for that 4,000 BTU bedroom, one bedroom. So this is a pretty good match with the exception of this little bit of short cycling. So the message for a one bedroom is to not do two heads, to do one head. And we picked an 06, but it's really important to look at what your max and your mins are, because even an 06 is giving you 8,700. Now the more challenging 2 and 3 bedroom. If a building owner says, I have a 3 bedrooms and 2 bedroom units, I want heating and cooling in every single bedroom, and I want heating and cooling in my living room, and I want heads in all those spaces. The load on this whole apartment is 8,000. If every single one of these rooms gets a head, the smallest head size is 7,000. So your indoor capacity already is at 28,000 BTUs, and you're way oversized. Let's see what it looks like if we went to ducted. So ducted would allow you to pick just one indoor coil and then send the cool and warm air to every space. The drawback of going from, so in this case, everybody has their own thermostat, but we know that it's going to be way, way, way oversized. So it's not going to work. Going to this, unfortunately, you're going to have one thermostat that controls this, unless you want to go and get more complicated with dampers that open and close. You could do a thermostat that is maybe in a common area so that it tries to pick up an average of all these spaces, but it's going to be one thermostat. This allows us to pick one indoor head that can better match that 8,000 and deliver air to all the spaces. So I looked at another Mitsubishi unit, and this is an 09. Our load is 8. And even the 09 has a rated at 12,000. But what we really want to know is how low can it go when it's pretty warm out? And how low, what can I get out of it when it's really cold out? I was able to look online at -5, the heating capacity. So this is a little, in this case, this was a graph that I had to look at. And on the bottom is the outdoor temperature, and the on the left side is the heating capacity. And if you were to go to -5 and go up at 70 degrees, it comes out to 32.5. So 32.5 of the max is 4160. So at -5, we're getting 4160, but the space needs 8,000 at -11. So we're off a little bit. Let's put this into the Neat tool and see what happens. I was able to put in the data at -5, and that's why it ends right there. The yellow cone is showing where the unit can perform, and the orange here is showing the building load. As you can see, at 5 degrees, the heat pump is still running, but it can't pick up 100% of the load. And after -5, because I didn't have any other data, it just assumes that it's not going to run, although it likely will run some. So this purple is all the supplemental heat that's needed, including up here. This little triangle is the heat pump is running and your supplemental heat is kicking on, which could be like a boiler or electric heat. Your short cycling starts at 30 degrees and goes up. And for the majority of the season, you know, the blue here, you're pretty okay, except for this short cycling. And although this looks like a lot of pink for supplemental heat, it's really, you know, look at these little blue bars. It's not a large percentage of your total heating. So I wanted to know if picking a unit that was an 09 with a fair amount of time in the purple, if I could size up to a bigger unit, and what would I gain from sizing up to a bigger unit and being able to operate more in the colder? Because this really is the smallest you can get. So I sized up to a 15, which gives you 18,000 rated. It can go down to 5,000 at 47. And then at -5, it can do 7,000, which is not very far off from the 8,000, which is the design. I put this into the tool. What I found was my short cycling went from 30 down to 27. And now my yellow cone of where it can perform versus the orange, which is my load, now there's just a teensy tiny amount of supplemental heat. And for the most part, this heat pump is going to meet the load of the space, a little bit more short cycling. So the question is there any benefit of going from the smaller size to the larger size to pick up more of the backup heat, eliminate the backup heat? So at the smaller size, there are 232 hours of backup heat. With the larger size, there was only 49% hours short cycling. Yeah, you definitely take a hit. And I did the calculation looking at the COP at the different outdoor temperatures and the amount of backup heat, assuming that this purple was straight electric. And what I come up with is the operating kilowatt hours, your energy usage isn't that significantly different between the two. I suspect the reason why this is a little bit higher is because there's 232 hours with straight electric heat, but you have more short cycling. So my message here for this ducted 2 or 3 bedroom unit is it's fine to go with the smaller size. The amount of short cycling is lower, which is way better for your equipment. And there's almost no energy penalty of going with a smaller unit. And you're going to spend less first cost on a smaller unit. My other message is you have to look at these charts to really understand which heat pump is going to work best for your space. Each manufacturer has hyperheat or there are units that you pay a premium to go in to be able to not lose capacity, going from 47 to 5, where it maintains its capacity the whole time. And then there's other ones which drop capacity, but you don't spend as much. So when designing a system, you have to figure out, do you want to spend more on maintaining capacity? How does that impact your short cycling? Versus, do you want to spend less and get a unit that doesn't do as much performance? And that's that, what's the word, capacity factor? Li-Ling, is that correct? Your capacity factor.
Maintenance?
Your what?
Capacity maintenance?
Capacity maintenance, yep. So in summary, if you have a studio or a 1 bedroom, we're not recommending that you do multiple indoor heads with 1 outdoor unit. We're recommending you do a single indoor to outdoor with some electric backup in the bedroom if needed. And you're talking about 5,000 to 7,000 per head. Don't oversize, don't do multiple heads. For 2 and 3 bedroom, don't put a head in each bedroom and one in the living room. It's going to result in a lot of short cycling and oversizing. We recommend doing either one in the living room and then doing backup heat, or doing a ducted system, which is ideal. You will spend more on ducting, $2,000 to $3,000, maybe more for ducting in an apartment, but you spend less on the first cost because you only have one indoor head and one outdoor head. I want to make a note about energy code. There is information in the energy code about the use of a backup electric heat. It is only allowed if you're using a cold climate heat pump. It is only allowed if you have a really good blower door test, and it's only allowed to come on below 5 degrees. So there are some requirements of your system if you choose to use backup electric heat. If you have an existing building and you're adding heat pumps, and you already have a backup heating system, it's usually more cost effective to stick with that backup heating system and potentially undersize your heat pumps so that you don't have the short cycling and that they're operating at their best possible during the majority of the heating season.
And Mary Jane, I just want to bring this back to a single family application. So that second line there, can you go back? Yeah. So the second line there, a 2 or 3 bedroom, that would be a standard house. If you can do an individual outdoor unit for each individual indoor unit, so this is called a 1-to-1 scenario, then you can have an indoor unit in each of these spaces. But what Mary Jane is saying over there in the recommendations column is don't attach more than one head to an outdoor unit, because then your outdoor unit is going to have to be too big. Whereas like 2 or 3 6,000 BTU an hour heat pumps, individually connected to their own outdoor unit, that's a good design for a single family. In multifamily, it wouldn't work because you just don't have space for all those outdoor units.
Right. If you have a 40 unit building and you want to do, and you've got some 2-bedroom units, that's 3 1-to-1 units per apartment. You're just going to have a whole roof filled with split heads that need to be cleaned every single year. It's just not cost effective for the owner of the building. And I think in terms of, yeah, it's a first cost nightmare and it's an operating nightmare. So is there another option besides mini splits? What is coming up next? We have found that a lot of our apartment and low-income housing developers are questioning whether or not mini splits are their best option. And that's one, because of the sizing issues, the short cycling, and the maintenance associated with having to take care of all of these units up on the roof, and the installation concerns with running line sets down 3 floors, down 4 floors, and connecting to all these units indoors. So what's coming up next is these through the wall self-contained units. So there's no ducting and there's no refrigerant line sets that you have to connect, and they just plug in, or you can hardwire them in, and they provide heating and cooling. There's also units that do heating, cooling, and ventilating all in one unit. So now you don't have to look at a central mechanical ventilation that's distributing through all the apartments. Some of these options can also work for single family homes. This last one, saddlebag double hung window retrofit option. This is something that is just being developed right now. It hasn't really hit the market yet, but when it does, it's going to be a huge opportunity for retrofit applications. And when I say retrofit, it's something that you can install yourself. You won't need a mechanical contractor. So these all-in-one units, they don't have an outside component. They just go through the wall. And there's a couple units on the market right now. The Epica is the one on the left, and it sits on, it can sit on an exterior wall, and it can also go, here it's showing on a interior partition wall, and this is showing it, the blue right here is showing it on just against an exterior wall. And it's doing the heating and cooling inside the unit. The compressor and the condenser are inside this unit, so there is no outdoor component. They are cold climate, and they are on the NEEP cold climate list. They're just not under mini splits. They're under packaged units or vertical packaged units. There's Olympia, this Olympia Splendid. This is also another option that we're seeing other states that aren't quite as cold as Vermont, because they don't go below 5 degrees. Well, the Epica unit does go well below 5 degrees. It goes down to -5. These units are not the cost of like a PTAC or a window AC. They're much more expensive. I would expect you're going to pay $4,000 to $6,000 for one of these units, but they're clean and they look nice, and they could work for multifamily housing. They could work for, you know, a mother-in-law's unit off the back of somebody's house. They could work in dormitories. The really exciting thing that we're seeing now is the combo unit, the one that's doing heating, cooling, and ventilating all in one. So the first one that we have seen installed in Vermont is this Minutair. It comes out of Canada, and it is a ducted system. You are bringing outside air in to do your ventilation as well as to do your condenser compressor. So there is no outside unit. Your heat rejection off your compressor and condenser is happening inside this box. The way it is able to do some heat recovery is that all of the exhaust air goes across the condenser before it leaves the building, before it leaves this unit. So instead of having to deal with -10 outdoor air, you've got some 70-degree air going across the condenser in the coldest part of winter. The Minutair unit, I like to call it a ventilation and cooling unit with some heat. What we have found that the electric 5 kW electric heat coil has to kick on somewhere in the 20s. So it's not really a true cold climate, but it's a great option where everybody gets their own heating, cooling, and ventilating per apartment. This could even work in a house. Then there's the Epica AIO unit, which is this unit right here. But there's an add-on heat recovery component, and that allows you to do the heating, the cooling, and ventilating all in one. The difference from the Minutair is that it actually has a little heat recovery core, and you can run it at 40, 60, and 80 CFM of outdoor air in its cold climate. So this really is the true all-in-one. It can do everything you need for one apartment, and I have an example of where it's being used. This is not an inexpensive piece of equipment. This is not an inexpensive piece of equipment. You're talking of probably $10,000 just for the equipment installed. This is probably even more because of all of they both have ducting, because they have to duct, pick up from the bathrooms and deliver to the bedrooms or the common hallways. There are also other units that would work in multifamily and probably not single family. There's Aldi's or also called Alds and Unilex and Omega. These are either hot water fan coils, so you have hot and cold water coming from a boiler or a chiller or an air to water heat pump or a ground source heat pump. And they have the ability to do heat recovery right in the unit. So they need to be located vertically, and they pull air from outside across the heat recovery core and are able to heat and cool the building. The same where you would have a water source heat pump inside this a vertical fan coil, and the water source means that you have to have water running around the building. So in these two, you need to have supplemental heating and cooling coming from somewhere, which could be ground source, it could be a pellet boiler, again, commercial applications. The most exciting is the saddlebag retrofit for heat pumps. This has come from New York Housing Authority, the Clean Heat for All Challenge. they put out an RFP asking for someone to develop these saddlebag type retrofits. There is a ton of housing in downtown New York City where you've got steam boilers, steam radiators, and they want to electrify and provide some air conditioning. And these units are available with natural refrigerants. They're available 120. You can plug them in. Some of the first pilots are happening within the United States to see how well they're working. And I figure in a couple years, they'll be available for the Vermont market as a retrofit application. They're really neat looking. They're very clean looking. And hopefully we'll be able to use them in some housing, maybe some public housing in Vermont. So why consider these options over split units? I think the biggest consideration for customers that have, you know, a 30 unit building with 35 mini splits is the maintenance is a huge one, and the not needing to do refrigerant line connection, which I think people are nervous about the amount of refrigerant lines that are going down into buildings and the amount of potential work in the future when those units are failed or they are at the end of their life and all the new types of refrigerants are on the market and you can't use the same refrigerant lines. There's no duct work unless you're doing those small ERVs. So in the overall, the amount of duct work that would normally be coming from a central rooftop ERV down to every apartment, that is, it takes up space, there's room for error, and it's not inexpensive. So if you're doing these individual units that have their own little ERVs, the amount of ductwork is really small. It's just from the bathroom, the bedroom, the living room. And a lot of customers do not want to have to deal with this whole roof filled with condensing units that have to be cleaned every single year. That doesn't mean that these units don't need to be cleaned. It's just that now you're cleaning filters inside these units, and maybe every 5 years or so, you may have to do some coil cleaning inside the units. And there's a substantial installation cost savings. The a mini split plus a central ERV, you're looking at, you know, 5,000 to 6,000 for the ERV, excuse me, for the mini split, and then eight for the ERV if you have a central ERV, about 8,000 per apartment. Versus going with one of these all packaged units, you could be in the $10,000 or less range. So the future is happening now. These Epica AIO units with the ERV, right in Burlington, if you get off of exit 14 to go to UVM, there was the old Holiday Inn. It's now being turned into housing and apartments, affordable market rate, as well as potentially a hotel. And they ended up going with this Epica AIO unit with an ERV. It's a vertical unit in the wall, and they have tested it. They have looked at its function at cold temperatures. They have looked at it from a noise perspective because it's on the highway. It's on the flight route to the airport, and it's got a heat pump in it, and they want to make sure that it wasn't too loud. And once it was installed and everything was, all the framing was put on it, they found it to be fine, and they're moving forward with it. So this is the biggest installation so far in Vermont. I know that there is at least another 4 or 5 projects in design that are considering this Epica AIO unit with the ERV over a mini split instead of going with the mini split and the central ERV. There's also the Talta Hotel and Cabins up in Stowe. They are building these little cabins, and each one of these cabins is going to have an AIO unit that does not have an ERV, but it's your cold climate. And instead of looking like kind of a crappy PTAC unit that you would find at a hotel, it's a very more modern, sleek looking unit. And then for ventilation, they're doing these mini ERVs which are made by TwinFresh, and they go right through the wall, and they have like this charging cartridge that flips from heating to cooling, from fresh air to exhaust air, fresh air to exhaust air, that are transferring the warm air onto a charging cartridge. All right, so that was the end of my slides. And we have questions. Which I can't see.
Thank you so much. We don't have anyone with raised hands right now. I just want to put a link in the chat for everyone. If you're not already an Efficiency Excellence Network member, please reach out to learn more and see whether or not you'd like to enroll in one of our trade groups. You can get additional support about incentives and technical assistance from our fabulous ECs, such as MJ and Li Ling, and our account managers. We are looking forward to posting our agenda for our Better Building by Design conference soon, probably towards the end of next month. And if you're an EEN member, we do have discounted rates for that. So another plug, another reason to enroll in the EEN. There's a lot of content today, a lot to go through. So please feel free to ask any questions that you have. I'm certain that if you are curious, then there are others that have similar questions as well.
I also wanted to say, if folks are just starting to use the NEAP tool and they need help, to reach out to either of us. Right after we gave this presentation at Better Buildings, I had 3 or 4 people call me within the next few days that were using the database and had some questions. And it made me so happy to know that we inspired people to at least take a look at the tool, at the database. You know, our goal is to help people make better decisions when it comes to selecting and sizing heat pumps. And the more we can do to ensure that the technology is implemented correctly, it's just better for the market overall, and it's better for our focus on electrification if we're getting systems installed that work well and aren't short cycling and aren't having issues.
Yeah, thank you for that. And if you